Hi, John here. Let's talk about the C++ Standard Thread Library. This library is pretty simple. I'm going to just talk about an introduction here today. We are going to go over how to create threads and how to clean up after they're done. And we're going to talk about something called a mutex lock, which is a pretty common thing you're going to need if you're going to write threads, okay? So let's first of all start with, why do you need threads, all right? Kind of slash what are they at the same time. So let's say we have a task to do, like we want to add up all the elements of this two-dimensional array. All right, you might just write a simple nested for loop and say for each row, and then for each column in a row, sum, equals sum plus, the element at the row and column. All right, using like a two-dimensional array of integers or something like that, and just sum them up one after another, right? Each row one at a time, da 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 da. When you get to the bottom, you've got your sum and you're on your merry way. Well, let's say you have 1,000 columns and 1,000,000 rows. That's 1 billion elements and 4 gigabytes of memory. That might take a little while to finish, right? And on your desktop, you got the shiny new PC with this fancy processor. Maybe it's got 16 cores in it. Well, why don't we try to do something with all 16 of those at once, in a divide and conquer? That's why, and that's what a thread is for. So in that scenario, what we would do is we'd say use each of the computer cores, right? Each of those can run a separate thread of execution, we say, independent of all the other ones. So maybe one of the CPU cores can add up this row here, right? Maybe we'll call that thread 1. And at the same time, another core can add up the second row, thread number 2, we'll say, all right? And now this can keep going on. If you have 3 or 4 or 5 or 10 or 20 or 100 cores, okay, you can have all these rows being summed together all at the same time, each one of them being done at a different core. Let's stick with just 2 for now because it'll muck up the diagram here, right? So how then do we make all this work, right? You've got this main function, and it's obvious what to do with a two-dimensional summing program, but what do you do about these threads? All right, so somehow we have to start a thread. So what do we got on our to-do list? Let's go with the how. All right, we have to start a thread for each, I'm going to put quotes around task or unit of work, right? And we have to, assign that unit of work to each thread. So then we have to assign a portion of the problem to each thread. Okay, when we're done, we have to combine the results from each thread. Okay, this is roughly what you need to do. And there's a really simple scenario here. So somehow we have to start a thread running and tell it to do row 0, sum up all the contents of row 0. Start another thread running and say you sum up the contents of all the elements on row number 1. And when they're done, what do they do, right? Well, then thread 1 might say, all right, I'm done with my row. Let's do the next row that nothing else is working on right now. So that's the assigning a portion of a problem to each thread, right? And there's many ways to do this. Like, for example, if you only have 2 threads, it might be that thread 1 just simply does all the even rows. Thread 2 might do all the odd rows. Okay, that's easy. Brain dead simple. You just count by 2s in the for loop for what row each one of these is going to do. They can all sum them up, and they'll have 2 separate sums. Well, they'll make partial sums, right? So when we're done, we might have like a thread 1 partial sum, in a variable sitting here. We might have thread 2 partial sum. Right, in this scenario where we had 1,000 columns and 1,000,000 rows, right? So that would be 500,000 rows in here worth of data, another 500,000 rows worth of data in this one down here. So when these two threads have completed everything, we'll have these two numbers. So something, when they're all done, has to add these two and get this gross sum, right? Okay, when we're done. That is the answer we would be looking for if we can dispatch the work like this. So let's focus on these three things and look at how the C++ standard thread library allows us to solve these three problems when dealing with something like this. All right, let's start with how do you just start one of these things going. Okay, so what do? We write a regular old C++ program, and we need to include the thread library definitions and stuff with that header file right there, okay? Now we have this, here's my main and then a function called foo here, all right? What are we doing down here? The main's going to start running, and the first thing it's going to do is print something. We can ask the thread library, how many cores are on this machine? And it'll just give us a number. So I'm going to print out here, here's how many cores, concurrent threads supported on my particular machine, carriage return, right? Then I'm going to create a thread, and this is really all there is to it. You say, hey, give me a thread. I'm going to call my, you then create an object that's a variable. I'm going to call it T0. That's going to represent a thread that's going to start running. And when I start that up, it's going to say, here, execute this function up here called foo, which is right here. And when you start it, pass it this argument, which I'm going to call it TID for my thread ID, and I'm going to just assign it a bunch of integers, thread 0, thread 1, and so on like that. So I'm going to create two thread objects. I'm going to call it T0 and T1. They're both going to execute the same function here, and each one of them is going to have a different value for this TID argument here. When it starts running, it's going to say thread, number such and so, I'm running now, and then it's going to print 20 times through a loop, hello from thread, whatever. And then it's going to print out its I. So hello from thread, 0, number 0, hello from thread 0, I equals number 1, and so on, until it gets up to 19, and then the loop ends and it comes down and says, okay, thread number such and so is now editing. So both of them are going to run the same thing at the same time. As soon as it's created, they start up right away, okay? Now, after I've started these two threads, there is the fact that, remember, main has a thread of its own. We have three threads of execution at this point. The operating system starts a thread going just to run main, right? Normally, you'd run a single-threaded program, okay? The single-threaded program creates a second thread. It creates a third thread, okay? So there's actually three threads running right now at this point. So the main thread does this to wait for thread 0 to finish doing whatever it's doing. Okay? How does it know it's done? Well, if this function here returns, then that thread terminates. Okay? And when main says join over here, what it's really saying is, let me know when this thread number 0 up here, it's code that is executing in foo up here. Let me know when that thing is done. Okay? That's what join does. Then let me know when thread number 1 is done. So this is how main waits for those threads to finish running. When they're done, it'll say, okay, main over here is now done and exiting. That's all this program's going to do. So let's run it. And okay, we can sort of recognize what's going on. First thing that happens is it says, hey, you've got 16 cores, so you can run 16 threads all at the same time on this computer. Okay? And then I start two threads. And remember, the first one's going to start going, and it says, hello, I'm, thread 0, and I'm starting up. And then it goes into this loop, and it starts printing thread 0, I equals whatever. And now, in the middle of that, it says thread 1 is now starting. Then it says, hello from thread 1, my I variable is 0, and then you see this extra 0 hiding over there, which is actually the 0 that was printed as part of this message up here that never really happened and never finished. Okay, and then you see hello from thread 1, its second message in its loop, and then it kind of starts working okay. At that point, we sort of see it going for a while, and after thread 1 gets over to number 11, it then kind of gets cut off, just like thread 0 did up here, and then you start seeing stuff from thread 0 get printed out, and here's the 12 here that should have been part of this message up there, and then you see another hello from thread 0, and it kind of goes back and forth. And some of these that have missing carriage returns, there's a carriage return that probably came after that 12 right there. And then you see some more output from thread number 1, and then another thing that gets cut off right in the middle of it. Okay, so you can clearly see it's going back and forth. Okay, is the point here. They're both running at the exact same time. And what's interesting to note here is that any time when this thing is printing like this, it could switch between these two threads, right? So sometimes it's like hello from thread, and then it doesn't say anything. And then you'll see something from the other thread, and then you'll see it continue with the thread ID and so on, right? So what happens is these really are running at the same time. And in fact, if we just run this program a couple of times, oops, if we run it a couple of times, you'll see it'll be very different every single time. All right, this is just based on what happens to be running on my computer right now and how busy it is. And, if there's a lot of work to be done, it might be only able to run a thread for a little while and then run off and do something else and then kind of come back again, right? I mean, I might have 16 cores, but if I'm running 20 different things at once, well, then, those 16 cores are already oversubscribed, okay? And you'll see it jumping around like this, okay? So anyway, the bottom line is these two threads run at the same time, and they are completely unsynchronized. That's the takeaway here, right? This guy can print as much or as little as it wants, followed by the other thread, and they'll just go back and forth. So you end up with a mess on the screen if you don't do any kind of synchronization between these two threads, okay? Now let's look at a variation of this. What if I want to, rather than just hard coding the number of threads that I want to run, I want to use a command line argument here. All right. Now, this is a really lazy way. A good application would actually check the value, have the proper usage statement in here. It might even have an optional command line argument to set this. I just hacked this thing in here like this. All right. If you wrote a real program, do better than just simply asserting that I have, one argument on my command line for the number of threads. But this simply protects me from weird errors if I forget to put the command line argument in there. So what's the difference between these two applications? When we just saw no changes up here at all, I include this vector header. I guess that's a change on the top, okay? But point is, there's no difference in foo here. So let's focus on the main. Same thing we saw last time. Make sure that I have two arguments. The first argument is actually the name of the program. So technically, this is one argument, all right? Even though it has a number 2 right there. Okay, so we create a vector, a C++ vector of pointers to threads. Last time we just created a thread for each one. We just had a hard variable sitting right there. And what I want to do here is I don't know in advance how many threads I want to run. I'm going to get it from the command line. I'm going to say I want this many threads to run. So I have to convert the string from the command line to an integer, right? And for that, that argument there, put it in a variable called num, okay? Then what I'm going to do is say I'm going to add a new thread. I'm going to construct a thread for each one of the threads that I was asked to create on the command line argument up here, okay? So for I equals 0 to however many I want, this is how you add an element to the end of a vector. If you're not familiar with the vector class, that's what that does, okay? So I say push back, push back, push back. I will have then put 3 elements into a vector. I would have used a regular old C array here, but remember, I don't really know in advance how big it's supposed to be, All right. So this is a handy way to do this. I can just keep adding as many as I want into this vector. And what I'm adding here, remember, is the address of a new thread object that is allocated in the heap. And when it's constructed, it's given the foo function as the thing to call, and I'm giving it I for the ID number that I want to pass into this foo function, the argument that I want to pass into the function, okay? So that's how I create as many as I want. Now, just like before, I wrote there's 3 threads here, but actually now there's n, right? There's actually what is there? There's num plus 1 is what that should have said, right? And in order to finish the job, I got to do this join, right? So how do you do that? Well, I'm going to go through all the elements in my vector, just like I did up here when I added them to the vector. This time I'm going to go ahead and I'm going to do a join for each one of the elements in there. And again, if you don't know how the vector really works, what you do is you got this dot at. This is a safe way. I could have just as either put threads open square bracket I, like a C array if I wanted to in here. But by saying dot at and putting the element number in here, what I'm doing is I'm telling the vector class to make sure I didn't screw up and give you an invalid number in here. You know, am I asking for an element past the end of the vector, right? And it'll stop my program and generate an error message if that's the case. So that's what that means right there, okay? So what is the value of an element in this array? If the array contains pointers to threads, it's a pointer to a thread. So I'm going to say join with that thread. At that point in time, I know the thread is no longer executing, and therefore I can delete the thread object out of the heap. Okay, if I don't do this, I'm leaking memory, right? I need to clean up when I'm done, right? I added it, I created it here. If I do a nude, I eventually need to see a delete, all right? So that's what I'm doing. I'm going to delete them all one at a time. Now, you'll notice that what I'm doing is deleting the thread object that's in the heap here. I am not removing it from the vector. I'm leaving the pointer in the vector. I don't care about that. I just need to make sure I got rid of this thread object up here, okay? Whose address is in this vector up here, all right? Just make sure that we're all following along here. When I'm done, I'm going to print out my main executing and return just like before. So this creates, num threads, and this joins and deletes those num threads. Now, why didn't I delete them or something like that in the last example? Well, it's because these are like a local variable here. It's deleted automatically when it goes out of scope, right? We all remember how that works, okay? So what's going to happen here is I delete all the ones that I created in here, and when I fall off the end of main and return down here, this vector will then be deleted. And along with the vector will be all the pointers to the threads. That will not delete the threads themselves, right? So I'm going to go ahead and do that in this loop. That's the whole point of this one here, right? So if I say make that program and I now run it, first thing I did is forget to put an argument in there. So this is an incredibly ugly usage statement, but at least I checked my arguments, right? So let's say we want to run it with 2 threads, all right? This is basically the same thing we saw before, and it's going back and forth. Let's say I want to only run 1 thread, okay? That should work fine. No problem, right? I go around the loop one and only one time. I create one and only one thread. It runs, and there's nothing around to interfere with its output, so it's perfectly clean. And when it ends, main reaps and cleans up the one and only one thread. And we can make sure that everything is all copacetic by doing a val grind on that. Okay, does it work? Yes, it says no leaks are possible. There's nothing in use. Everything was cleaned up, all right? We can also do this for thread 1 if you're interested, just to make sure that one worked okay too. That one's fine as well. Like I said, it's because those were local variables in thread 1, and in thread 1A here, we are need to clean up all the ones from the heap, all right? So that's what we're doing in here, right? All right, so far so good. We know how to start a thread for each one of the tasks that we want to create. I suppose we should also say, and, know when it's done. Know when done. So let's look at a common way to diagram what you just saw, right? So we have this main here. And normally you represent a thread like, it's like a piece of sewing thread lying on a table. So there's a thread, okay? There's a thread of execution. what does main do? It does stuff, right? Then it creates a new thread, all right? So it's going to create T1, okay? At that point in time, thread number 1 starts running. Then it's going to create thread 2, okay? At that point, thread 2 is running over here. So this is like thread 1, this one's thread 2, and they're both running, and they're going to do whatever they're going to do. They're running the foo function we just saw here, okay? Now, a main has nothing else to do at this point in the example that we just saw. If we run it with a command line, I put 7 or 8 or 10 in here, it'll just keep creating more and more and more, right? And they'll all print out their 20 lines of output, and they'll all draw all over each other as it goes. So for however many it's going to start, when it's done, it says it joins thread 1, and then it's going to say join thread 2. Or I guess my variable names in the program was thread 0 and 1, but I think you can follow along here, right? So what does this mean? This means that the main will stop and wait until this thread of execution is complete. Let me grab another color here. So what happens there is we can say this joins back in like this. We create it. When it's done, we say join. Okay, you can say join before it's done. As you can see here, in this example, I've drawn that main might actually do a join on thread 2 before it's even done. And in our particular code example, that's definitely the case because there's nothing for main to do while these are printing on the screen, which is something that takes a very long time. All right, so thread 1 and 2 are created. Thread 1 is joined here. Maybe it's done first, maybe it's not. Thread 2, this thing has to wait until here for thread 2 is done. So this is one type of synchronization that we need to be able to do. We need to know when these are done, okay? So that's one kind of collaboration that we see happening between threads, all right? Down here, we saw main then print some stuff out, and then it returned, right? So this is roughly what's happening in this program. Now, let's think about what happens when we're printing on the screen and we see stuff all over the place, right? When thread 1 runs, it does so indiscriminately without any regard to what thread 2 might be doing. So it might be printing things along all through here. Thread 2 prints things all along down through here, and they're interleaved everywhere. That's actually really what we want if you think about it, right? But there are times when you want to say, look, I don't really want these two to run completely autonomously because it's messing up my output. What we would like to do is each time thread 1 prints something, it prints the whole message out in its entirety. And if thread 2 comes along and wants to do the same thing at the same time, we lock it out. We make it wait. We make it stall, okay? So how then can thread 1 come through here and say, look, I'm writing to the screen right now. Don't let anybody else do it, right? That's what a mutual exclusion semaphore is for. This is what we call a lock. And this thing will say, look, stop a thread if another thread has, a lot of time we'll say has or holds the mutex lock. All right, we can create as many locks as we want. These things represent a specific resource. So use a mutex lock. What does it do? It does this, right? I can have a plurality of these things. Create many, either, or few, as needed. All right. And what we're going to do now is we're going to create one that will reflect the screen. All right. So let's say I want to lock the screen. Okay. So what happens is when thread 1 comes along and wants to print something, he'll say, all right, I'm going to lock a mutual exclusion semaphore that represents the screen from the standpoint of this program. Okay. So I'm going to just create this. It isn't actually related to the screen in any way. It just has a role that I ascribe to it based on convention in my program. So I'm going to create something like a print lock or a standard output printing lock or something, whatever I want to call it. I'm going to create a mutex, and I'm going to use it for that purpose in my program. So when thread 1 comes along, he's going to say, I want to print something. He's going to lock my lock that represents the screen. He's going to print what he wants, and then he's going to unlock it. And that'll prevent task 2 from printing anything while task 1 holds that lock. So what the logic here will be is something like looks like this: lock, maybe it'll be like screen. All right, then we'll print, we'll say see out, blah, 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 and then we'll say screen, unlock. So if thread 1 and thread 2 are trying to print at the same time, and we absolutely know that's what's happening because we can see it on our screen, this will cause whatever thread grabs this lock first to run and print anything it wants until it's done. And then when that thread that locked it unlocks it, the other thread can start running. Okay? So then thread 1 might come back around and lock it again to print more stuff, and then unlock it, and maybe thread 2 comes along, and so on. Now, the amount of work you want to do when you hold this lock is incredibly dependent on your application and how you want to optimize the situation. So let's start with the simplest possible solution here and work up from there. This is thread 2 now, okay? Now, notice I added this pound include for mutex in here. We look at the code, the main should be exactly the same as the last one. We print out the number of cores, we check to see if we got our argument, we create our threads, we clean up when we're done, and we print a message down here. What are the changes? Let's look at foo here. Okay, nice simple solution. Just lock up here. This is how you create a mutual exclusion semaphore, and it'll initialize it and everything else. You just stick it up there. And what you do is the thread just simply says lock, you do whatever you want to do, and then you say unlock. Now, if I do it like this, if you think about it, I'm going to start up 2 threads. Right down here, they're going to lock this semaphore, loop and run to completion, and then unlock the semaphore. And we're going to see this is not exactly what we want. Okay? Why? Because they're not really going to allow both of them to get any work done at the same time. And of course, if I have to put in an argument, it will help, right? So what happens here? Well, what we've done is we've created a situation where one thread number 0, starts running, goes all the way until it's done, and then and only then does the other thread start running. Okay? Because the first thread that gets that lock is the one that's going to run in its entirety the way we've written it. Then free up the lock, release the lock, unlock the lock, however we want to say that. And then whatever the second thread is that comes along will start running at that time. Now, if you do this multiple times, we'll find eventually they'll actually run in different orders. You'll still see some randomness in here. But what's going to happen is most likely the thread created first will start first. But once in a blue moon, you'll see it happen in another order. Now, it might actually be that you would need to run a few more threads. Now you can see it changing. I just started it with 3 threads. Interesting that thread number, we got? Thread 0 starts, then thread 1, then thread 2. So they do run one after another in the order that I created them. But if you do it enough times, you'll see that they actually don't run in that same order every single time. That one, you just saw it change in there, right? So here we see one where we started up 3 and in thread 0 ran to completion, then thread 2 ran to completion, then thread 1. And there's some randomness in there because that's the luck of the draw given how your operating system works. All right, so what happened there? When we said, we started up our main, we started up thread 0, right? We create thread 0. What happens? Thread 0 runs. It prints out its stuff, right? Let's go with a different color here. He locks, he unlocks, right? He locks, he goes into a loop, prints out 20 messages, and he unlocks. Right? Thread 1, when thread 1 starts in main, it's sitting over here, okay? First thing he does, he comes down here, and he says, okay, I need to do a lock so I can print out my stuff. Can't do anything because the lock is already held by thread 0 here. So it's not going to start until it gets the lock there. Then it can print out all of its messages here. And then it can unlock over there. Okay? Thread 2. What happens there? Thread 2 starts up. It's going to run a little bit. It's going to say it needs to lock. The thread 1 has it right now. And in this example here, if thread 1 is the second one who gets granted access to it, right? Thread 2 can't get access to it until all the way down here. So thread 2 has to wait until way down there. It can then print out its stuff there. It can then release the lock down here, right? So main says, thread 0 join. And it can't do anything until here. So maybe we'll use purple, right? So when this one's done, main can then wake up and join with thread number 1. So it says thread 1 join. And it can't do anything until thread 1 is done. There. Then it says thread 2 join. Right? And it's not until thread 2 is done that this join will complete. Okay? At which time main can print out its message and return back to the operating system. Okay? So this is really how this program is running. And this is this is terrible. You don't want to do this. I mean, it would take just as long. Look what's happening. We're printing out all the messages from task 0 here. This isn't doing anything at all. We then print out all the messages from task 1 right here. And this isn't doing anything either. So he doesn't start printing his messages until down here. It'd be just the same to just print all the messages in main because they all go an entirety here, this entirety after that, and so on. So this is a terrible way to write a multi-threaded app, other than to point out that it is a multi-threaded app, okay? So let's look at how to do a better job of this. Instead of this, let's try doing something more like this. All right, let's put a line here. Let's show what if instead of working this way, we don't have to worry so much about main. We know how the joins work, okay? So let's just look and see what happens when we start these threads, all right? This will be example thread number 3. All right, so we're going to convert this to something better. Let's say instead of doing that, we start up task 0 here, thread 0. And it runs, right? And instead of locking and then printing everything out, it'll lock and just print 1, okay? Then it'll unlock, okay? Now when task 1 comes along over here, it too needs to lock. But it's going to turn out it'll get the lock right there. It can then print its 1 item out. And then it can unlock here, right? Then eventually thread 2 over here starts running, and it's going to do the same thing. It needs a lock, and it won't get it until this one's done right there, okay? He's going to then just print out 1 and only 1 item, and then unlock here. All right, so now what happens? Well, thread 0 can go around its loop, relock again, right? It could print 1 item out, and it can unlock. Let me draw them like this so we can show the tenure of these locks, okay? So this one here is locked when it prints that one. This one here is a lock around the time it prints this one, okay? Now, let's say thread 1 obviously wants to lock again. It has to wait until this is done over here. And this also wants to print again. So they're all going to try and lock, print, unlock. Lock, print, unlock. Well, what's going to happen is we're going to see these things kind of line up like this. This one will have to wait a long time maybe down here it'll finally get the lock, and then it can print out something. And because these guys are holding the locks the whole time, the main has to wait until down here, or the main, or rather, I should say task 0 over there has to wait until down here, and so on. So what we've got now is we've increased the granularity of the lock, right? Do we want to lock for each individual message that comes out on the screen, or do we want to lock for the entire loop? Okay, that's the difference between these two things here. And it really boils down to the needs of your application. This is usually never a useful solution because it's easier to just print everything out in main because it'll take just the same amount of time anyway. So if the work that you do, which is these blue lines in here, it takes a little bit of while relative to the amount of time it takes to lock and unlock, right? So there's overhead is the point. How much time do you waste doing a lock and then unlocking, only to turn around and relock, do some work and unlock? Well, if it takes more time to fiddle with the locks than it does to just do the work, this might be okay. Or maybe you would, instead of doing one thing every time you lock it, maybe you do 2 or 3 in here. All right. So the idea is you want to have enough work once you get this lock to make it worth the overhead of managing these locks. Okay. But you don't want to hold the lock so long that you end up starving all these other threads and preventing them from doing any useful work, making any progress over just writing a single stinking loop in your main to begin with. All right. So there's this way off, pros and cons of how much work you want to do every time you grab a lock. All right. Well, let's look and see what the code looks like if we do it like this. Okay. So what happens now? I think the main has not changed at all. Okay. The only difference is we're playing some more games with these locks in our foo function up here. Look what happens. We grab the lock, we print one line of code. Then we unlock it. Because remember when we ran, thread 1, the first example, what happened was we were printing parts of a line and it was difficult to read, okay? Now what we're going to do is we're going to grab a lock and then we're going to wait until all this printing is done and the carriage return that goes out. Then we're going to unlock it. Then we can go into our loop. And each time we go through our loop, we're going to say grab a lock, print one line, and unlock it. Now we're going to go back up to the loop and say, are we done yet? No. Okay, grab a lock, print one line, unlock. When we're all done, we're going to grab the lock. We're going to say, hello, I'm now done, and unlock it again. So this is a much finer grain, right? And how we're using this lock, right? We're going to lock each little individual things, okay? By the way, if you have a one lock up here, and then you do everything, and then you have the one unlock down there, that is what we call big lock, okay? This is not big lock. Big lock refers to the fact that you're lazy, you just threw a lock around every single thing in there. It's your first draft. That's when you usually see that. So when people say, hey, I'm using big lock for this app, what they're really saying is, here's my first release. I just stuck it around the whole thing to make sure and test all the code down here that I can start up and shut down all those threads. I'm not gaining any real performance advantage out of this, but I am getting the mechanics all set up, okay? So that's what they mean when they say big lock, okay? This is not a big lock application, all right? So let's go ahead and compile it up. And once again, I forgot the argument. See, it's a good thing to check your command line arguments every time. Okay, so what I do, I started up 2 threads. It says 16 are going. I started up my 2 threads. Now look what's going on. I have all readable output, a whole line each time, and I get a couple of 1s, and then thread 0 runs a little bit, and we can see it going back and forth now. Thread run prints a few things, and then until it's done, and now there's really nothing left for thread 1 to do anymore. So thread 0 is going to easily get the mutex now every time until it's done, and we end up finishing the whole program. So what happens if I run it with 3 threads or more, right? I get no problem here, right? So now what happens here? Thread 0, look at that. On a coincidence, the whole thing finished because it took a little while to start up the next thread, okay? This is kind of interesting. Thread 0 starts, right? What happens after the whole thing is done? Thread 2 starts. What happened to thread 1? Well, thread 1 started running, but it never got the mutex. It can't start printing until it gets way down here, right? So, like I said, you get luck of the draw. So you got thread 0 ran the whole thing, 2 then runs, then some of 1, then more of 2, then more of 1, and then 1's done, and then you go back and finish more 2, and it'll just jump back and forth like that every time you do one of these things. That's interesting. This is purely coincidence that all of 0, all of 1, and all of 2 ran one after another. Again, that can happen. I mean, if you think about it, there's just not that much for one thread to do in this particular application. If it printed out thousands, it would definitely jump back and forth every single time we would run this example. But in this case, I got an incredibly fast CPU. One of these entire threads can sneak in and finish everything it's supposed to do all at once, because this machine is pretty darn powerful. All right, but of course that's not always the case. It does jump around a lot, as you can. There's one jumping around a whole lot right there. Okay. All right. So what do we know so far? We know that if we use really coarse locking, we end up doing these things one after another. This is end up serial. This is processed one after another. If we put them with really fine grain locks, this is running in parallel. Okay. The art of tuning, which was best, right? This is usually never what you want. You never really want to serialize everything because it's just worthless. It's pointless. Just do it all in one fill. Just do it all in one loop over here. Now, this example over here might work best if you lock and do one little thing at a time, and you lock it for each individual one. Or maybe you want to lock it and do a couple at once. This is up. It totally depends on how the application works, how much CPU time it takes to do all these things, and what's really happening, and how much does it interact with each other when it's doing this work. The art of getting this all right is called load balancing. Okay. This is a never-ending task. It's, when you have a dynamic load, right? Well, in this particular example, all we're really doing is printing something on the screen, and we're not doing anything other than printing. So we always have to hold a lock to do the work anyway, right? You might argue that it'll still take this long with or without the locks. All right, that's true. But if there's other work you can do between here that doesn't require you to hold the lock, okay? There's work you got to do that is interfering with other threads, and then there's work that you can do that does not interfere with other threads. And when you interleave these things back and forth, you start getting increased parallelism. And that is really the optimum case, right? This was an extreme case, an extreme example of the worst case situation. And that is where everything you do has to be done while you're holding a lock, right? Whether you do it this way or this way, if there's no activity happening outside the lock, then it's probably going to take the same amount of time anyway. But as you start doing more outside of the lock, when you're not holding on to it, you get better interleaving between the threads and you get more work done at the same time. You improve your parallelism and you improve the overall load balancing, right? So the goal of load balancing is to have every core busy all the time and never waiting. That's the optimum case, okay? The worst thing you can do is have all of them waiting all the time except for one, and then have them all run once after another, all right? In this incredibly trivial app, the only work that is happening outside of these locked regions down here, okay, is work that has to do with the for loop, right? It's the asking if the for loop is done running. If it needs to keep going, it locks, prints something, and unlocks. Then it goes around and asks, hey, is there more work to do? Okay, there is. Then what is it going to do? It needs to lock, do the work, unlock. Then there's a little bit of work here to ask, should I do some more work? Okay, maybe I should, or maybe I'm done, or whatever it's going to do at that time, okay? So the application that we're looking at is so trivial that it's really tough to get a good amount of parallelism out of here. But what we have shown is that even with very little parallelism and having a fine grain lock, you can definitely see that we're jumping around back and forth between all these threads, and they're all getting some work done. They're all getting progress, and they're interleaving between each other, which is, what you want to do is your first step towards getting good load balancing and a good degree of parallelism. All right. All right. We've got this under control. Okay. How do we deal with this? All right. We can start these tasks. We know how to shut them down. Okay. How do you then decide what each one of them should do? I mean, if you're not just printing stuff out, I mean, that's just hello world, right? But if we want to say, look, you get this much, you get that much, and so on, we can do a couple of things. Like I said, if you only have 2 threads, you can use even and odd, or if you have 3, you can do multiples of 3, right? That's one way to do it. But what quite often is the case, the amount of work you need to do varies. Okay, and the example we're going to look at, it doesn't vary. It's the super duper 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 trivial example here. However, in the real world examples, it might be that whatever this task is to, we're just summing these, all right? But let's say they're, arbitrarily complex function that has to be called for each one of these, a convolution of some kind, okay? And let's say that convolution depends on the values of these variables, all right? If that's the case, the amount of time it takes to add up one row of numbers may be radically different than the amount of time it takes to add up another row of numbers. And these things could end up, maybe thread 1 gets done way before thread 2 is done, and thread 1 then starts the next row here, and thread 2 is still up here, and thread 1 would, all right, I'll move on to this one down here, and so on. Thread 1 might just do a bunch of in here, and then thread 2 might say, okay, I'm finally done. It'll then start executing down here, right? Well, that's another way to do it. When you know that you're doing work where you guarantee the amount of time you spend on each one of these cells is exactly the same as any other cell by any other thread, you can get by with just doing like an even row and an odd row like this, okay? However, if that's not the case, then what has to happen for optimum usage, you want to prevent one thread from getting all done and saying, okay, I'm done, and having another one sit here taking forever to finish its work. And that happens a lot when you're writing these multi-threaded apps when you have an imbalanced load. So the notion of deciding what each thread should do can get complicated, all right? So rather than just doing evens and odds, let's look at the kind of thing we need to do to figure out which each one of these, if thread 1 does get done first, what should it do next? Should it just go on to the next, even row or the next odd row or whatever? Or should it, try and grab as many rows as it can until thread 2 is done, and then thread 2 will just grab the one after the one that thread 1 is currently working on and go along that way, okay? That latter approach is generally better if it's easy to do, because it's not going to fall prey to the situation where one thread just takes really long on one row while the other one just races to the end down here and then can't go back and help out the first thread by participating in the other rows. Now, I would argue that if thread 1 does, like, the first row is row 0, right? Then it's an even number. So if thread 1 does all the evens and thread 2 does all the odds, what you would do is you would simply say thread 1 starts with, we would just assign it row number 0, okay? And it would simply repeatedly add 2 to that value until it's done, okay? Thread 2 over here would be given the number 1 for its first row, and when it's done with that, it would add 2 each time through the loop. That's a pretty trivial, straightforward program to solve. I'll leave that as a task for the viewer. Let's move on to the other one, where at the end of each row, thread 1 has to figure out what thread 2 is doing and decide what row should it be doing next. So in thread example number 4, what we're going to do is we're going to have a counter. And for whatever reason, I decided it was easier to count down instead of up. So I'm going to start it equal to like the number of rows that we want to add up. Okay. And what's going to happen is when we go around our loop, we need to decide what the row number is going to be. So we got a 0 and a 1 and a 2 and a 3 and so on. Maybe there's 1,000. Okay. And there's 1,000 rows in this example. All right. So Counter equals rows. That would set the counter to 1,000. So what do we need to do in our program? So that foo function, right? You set up and do its other stuff, right? Its main thing is going to have this loop here, right? So let's not worry about adding up anything for this example. Let's just figure out how to decide what row we want to add up, okay? We can certainly iterate over the columns and sum them up, okay? But how do we figure out which row each one of these threads is going to use? So maybe we'll do something like this, right? While what? Counter is greater than 0. Okay, right? The very last row in the whole table would be row number 0. Okay, and then we would be done. So I'm going to say while there's counter greater than 0, maybe I can do something like this. I'll just say minus minus counter. Right? Because this would be the row that I need to work on. Okay, this is my row. Okay, because remember, when you're dealing with an array, of course I labeled this poorly, this would be an array that has 1,001 rows in it. Because there's row number 0 up here, all right? So in this scenario, I'd set it to 1,001, okay? So if this was, instead of that, it would 999 is what I should have written there, okay? 0 to 999, total of 1,000, right? So when I set counter equal to rows up here, that would be 1,000, okay? So the first one I need to process, I have to subtract 1 from it, okay? Now I can say like for, whatever, I equals 0, I less than, number of calls, and do my adding, blah, 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 add, sum. Okay? And then I just go back around to the top of the loop. Right? What am I really adding and summing, right? I would have clearly a two-dimensional array somewhere, and the counter would be my row number, and I would be the column number, right, to do the adding. We don't need to get into this. Let's just focus on how we figure out our rows, okay? Now, if this is going to be done at the same time in 2 separate threads, we got a bit of a problem, right? Because they're both going to be decrementing it, and who's going to do it first? And what if one thread decrements the counter while the other one's using it as its row number? All of a sudden, it's going to be adding up all the wrong rows. We got to figure out how to synchronize all this stuff. All right, we can put big lock in here, which is, whatever. That really won't solve the problem, as we said before. It'll just serialize the whole thing and not give us any real parallelism. What we really want to do is make sure that this code here is synchronized. And once that's done, we can do all the summing. We don't need to hold a lock for this. Okay? This is no lock. Why? Because if I'm adding up one single row in one thread here, and another thread is adding up this row down here, these two have absolutely nothing to conflict with. All the data in here is completely independent from all the data in the second row. It's all in one matrix, but that's irrelevant. It's each individual integer in this particular situation would be a separate value in a separate memory location, and there's really no way to get for these things to stomp on each other's feet as long as they all sum up different rows, okay? So the idea is find the row and then just sum up all the columns in that row, and then go back and lock the situation down, find the row it needs, and then sum up that row, and so on. And when it's totally done, it can take its sum of whatever number of rows it may have added together and contribute it to the gross grand total sum. Okay, so here's our first attempt here, all right? You're going to see this is not correct, so I want to make sure that you see that. Don't copy this code down and expect it to work. This is code that will break, okay? Let's look at the main real quick. Did I do anything interesting down here? I've got a vector of threads. I do the usual thing. I did that. Aha, I did make a small change here, okay? So see this T count resize right here? That's sneaking in there, and here's me adding up all the work. Remember I said at the end somehow you have to contribute all the sums together, right? So let's take a close look at what's happening in here and how this all I've done here is I've created this one new vector called, which is the total count. What this is going to do is it's going to represent how many rows each one of the threads is going to do the summing on. I'm not doing the summing in here because we don't need to worry about that. That we can add later on. Let's just figure out how to select rows and assign them to each thread. That's all we're doing in here, okay? So I'm going to create an object called tCount. It's up here at the top of the file. See this right here? It's called tCount. Here's my counter. Like I said, initialize it to some value up there. And we'll see what happens if we don't do volatility right. All right, we'll get there soon enough. All right, but right now let's look at this tCount. Right, I got a vector of integers that's called tCount, and as defined right here, it has nothing in it. It is empty. There are no elements. Okay, so what happens down here in main is I have to resize that vector. So there's one element in that vector for each thread, right? Because num is the number of threads. And I want to initialize each one of those elements in that vector to 0. Okay, so if I say run 2 threads, this will resize it to have 2 elements, and it'll set them both to 0. Okay? You've seen this before. I then initialize this accumulator down here for the total amount of work. Well, this is going to be the total number of rows that all threads together have processed. Okay? We already know how this works here. Okay? And what we're going to do is in this loop, while we're waiting, we have to wait until it's done because we don't know how much it's done until it's finished, right? We're going to just simply add up the tCount element for each thread. Okay, we're going to see that the foo function at the end of the foo function, the last thing it's going to do, it's going to poke into this tCount vector, the total number of rows that each one of the thread each thread had was assigned. Okay, and down here, instead of just simply saying, "Oh, I'm exiting now," I'm going to also print out the total number of work. All right, so this is kind of a debugging aid. All right, we know we better do whatever I set up here, 1,000 or 10,000, or heck, that's 100,000. Okay, so the total better add up to this 100,000. Right, we better see row 0 through 99999. Okay. Let's look at what we do in foo here. Startup, no change. The finishing down here, mostly no change. But one of the things it does, I print out the total number of count of elements that this particular thread was assigned. Okay, so here's this loop. Just like I said before, they say, well, while counter is greater than 0, I know there's more rows to be processed, so I'm going to subtract 1 from it. Because remember, we got to get the order of operations right here. I set the counter to 100,000. Presumably, there would be a matrix with 100,000 rows. Those rows are numbered from 0 to 99999. So what happens is, starting at 100,000, the first thing I need to do is subtract 1 from the counter. And at this point, counter represents my row to sum. Okay, I should say sum next, right? Because it's going to do the row. When it's done with that row, it's going to say, okay, I did a row. So what it's going to do is it's going to use the ID number that was passed into foo. Because remember, I passed in a 0 and a 1 and a 2 for however many threads there are. So I can say, look, in this vector up here, add 1 to the element that represents the total number of rows that this thread processed. Okay, now I'm not going to process the rows at all. I'm going to just go through the counter and just say, okay, I counted it. Here's the row I want. It would be in this variable, presumably. And I just say, okay, I did 1. And if I wanted, I could print out, okay, as it goes, maybe this is the work that the thread is really doing. And I'm going to print something, so I'm going to go ahead and do this nice little lock mechanism again so that the threads don't, spew all over the screen. All right, this is currently commented out. Let's go ahead and turn it on. Of course, there's 100,000 rows in this program. It's going to print a lot when we run this, okay? So if we fired up 2 threads, presumably one of the threads would get roughly half of the rows, and another thread would get the other half of the rows, okay? And we've got this counter, and we actually print out the counter down here, okay? And we should see one thread processing some set of rows, and another thread processing a completely different set of rows, not necessarily exactly in order, not exactly even and odd, but roughly perhaps about the same, because we're really not doing any other work. They're both doing the exact same amount of instructions if you think about it. It shouldn't be that one thread has more to do and the other one has less, all right? So it'll just be the luck of randomness, all right? But it should be roughly similar. So if we run this process here, what's going to happen? First thing, I'm going to forget to put the command line argument in there again. Okay, so what do we got going on here? Not bad. Okay, so we have the total count that one process did, one thread, I should say, did this many. Another one did this many. They both did this much total work while it was being added together in that vector at the top of the code. This is great. We can see thread 0, thread 1, they're going back and forth. Problem solved. All is well. And as is always the case, when you finish your program, you come along and you say, okay, time to give it to whoever paid me all this great money to do this awesome work. And you remove your debugging statement, and then you run it again, and you, what the heck is going on there? How can one thread do 94,000 and another one can do almost all of them for a total of almost double the total amount of something obviously is wrong here, okay? In reality, presumably, they're both doing the same rows, some of the same rows, right? Not exactly perfect, but some of the rows are being done by each of these two threads and duplicate, right? So you might think, okay, well, I'll turn my debugging back on. Maybe I didn't notice that before, or maybe I got to run it a couple of times and make sure that all is well in there. And if I do this over and over again, you just saw sometimes it does 100,001, sometimes it does 100,000. I happen to know it could just be pretty arbitrary. Here's 100,005. So if we look really closely in here, and unfortunately we got to go through 100,000 just print messages in here. Hopefully we just accidentally find one. Wouldn't that be nice? Where presumably one of these threads must be doing the same count number, same row number as the other thread, okay? And maybe we can find one in here if we look close. No, not really. It's pretty clean there. I guarantee you that it is. I mean, how can it add up to such a big number, right? Well, there's two problems with this code. One is that this variable is not declared as volatile, right? Remember what volatile does. It tells the compiler every time you use this variable, you need to go in memory over here and get the current value that variable has. In other words, you can't just say, oh, first time I use it, load it into a register, and then just leave it in that register while I'm going around and around and around in this loop as, an optimization. Because the compiler doesn't know that other threads are using the same variable at the same time. It can't know. Okay? How would it? Okay? So what happens is this code right here, most likely, loads this counter variable into a register and it stays there for a long time. And it could go around and around and around and around, around this loop a lot. And when the loop is done, then it can store the updated value back into this variable. And if you think about it, if one thread loads it one time and it starts at 100,000, and another thread comes along in here and loads it one time, it's going to also get the 100,000, assuming they both start exactly at the same time. Okay? And if neither of them ever actually stores this back into memory when it does this subtraction right here, they're both going to do 100,000 total. They're both going to do every row. We're going to do twice the amount of work that we really want to, is what's going to happen. And then when it's done, it's going to say, okay, this will have counted off 100,000 rows. Then the other one will do the same thing and tick off 100,000 rows. That's why those sums are darn near double what they should be. Okay? This is roughly what's happening. There's another problem also with this code. If it asks, is the counter greater than 0? And it turns out, yes, it is. And let's say the counter is currently set to 1. This thread comes along and says, okay, I'll dutifully decrement it, and he gets 0. And that's fine because row number 0 is a row that we want to process. That's why I put the subtraction in here first. Presumably the work would be down here, or the work would be between this and the T count. It doesn't really matter. First thing you need to do is subtract 1 so that you don't actually process that row, because the last row is 99999, okay? So this is right, but the problem is if the thread number 2 comes along and he grabs the counter and he sees it's 1, thread 1 decrements it down to 0 right here. And let's say we did it the right way and we made it volatile, okay? That way, every single time it does this, it stores it back right away, okay? But in this scenario, when they both looked at it up here, it was 1. If both threads see counter equal 1 at the same time, they're both going to subtract 1 from it and get 0. And yeah, they'll store the 0 back in there. Then the other thread will come in here and store a 0 back in there. And they'll both run row 0 and print this out down here. So volatile will help, okay, as we'll see here. Right, we actually have the right amount of work. Wow, maybe it solved our problem, you know. Look at that. Okay, not bad. And again, you say, okay, I'm all done. Yeah, I've tested it. I ran it 4 times. Of course it's perfect. What could possibly change? Remove your debugging code and... first of all, what the heck is that? Think about it. When a thread is done, it's okay, I did all these rows. It's still dang near half. It's still doing like double the work, okay? But how in the world could the count be this? Sometimes the count is -1, other times it's 0. What the heck is going on here, all right? I mean, you went ahead and you did all your homework and you said, oh, I know how to use volatile. Make sure everybody's sharing everything and don't hold it in a register. Get it back in memory right away. Well, it's related to the problem I already pointed out. We're not really synchronizing the threads. We're doing a better job, but we're not doing a great job, okay? So what do we need to do? As I said before, we need to synchronize looking at the counter variable, making a decision, subtracting 1 from that variable, and storing it back in memory. This all has to happen in one big atomic thing. This is what these mutex locks are for. If we can use a mutex lock somehow around kind of a half a while loop, which is kind of a weird thing to do if you think about it, and then the other half down here can be done without holding a semaphore that we use to guard this counter. In other words, we can create a mutual exclusion semaphore up here. It says if you ever want to look at the counter, you ever want to change the counter, you want to do anything with the counter at all, first thing you do is you lock a special semaphore that we're going to create just to represent the use of this counter. You do everything you're going to do, then you unlock that special semaphore. When you're done with that, you can go off and do any amount of work you want down here, knowing that the row that the counter variable represented is the one you need to be processing. So how do you do this, okay? Well, you got to be kind of careful and make sure you get all the order of operations just right here. Let's first start by looking at the main. Did we change anything down here? No, we did not. Okay, this is again counting the total amount of work, and each one of the threads that runs around this loop is going to say, here's some work that I'm doing, and so on. What is going on up here? So we see some stuff going on in this foo function here. We're also going to see some more stuff up on top. So what did I do? I added this mutex up here, and that's going to be used exactly the same way as the standard out lock did when we want to make sure our print lines don't get all munged up. But we have a kind of a chicken and egg thing going on here. Let's look at our while loop here for a minute. This used to be real simple. Now it's ugly and complicated. What do we got to do here? Well, first of all, we can't ask about the counter. Can't touch it, can't look at it, can't modify it unless we have a lock. And yes, I know there's many ways to do this. I could actually do a lock up here and unlock it and relock it. And let's keep it really simple here, okay? This is a really simple way to do this. We start with a Boolean flag. And the flag, the only purpose this flag exists for is to say, look, am I done yet? It's nice to have a variable for this. You could use the counter variable or a copy of the counter variable, as I got in here, to do a double purpose kind of a thing, but that's not the most friendly and user understandable code, okay? So what I'm going to do is I'm going to create a single Boolean variable whose sole purpose is to become true when I'm done. Okay, no confusion whatsoever. Am I done? Am I not done? Keep going, right? Am I done? And stop and go to the bottom, all right? That's the whole purpose of this variable. The purpose of this thing is you'll see when we want to use this counter, remember what I said, you have to hold this lock. If you look at it, you compare it, you subtract one from it, no matter what you do, if you touch it in any way, you must first lock the mutex that by convention only in this application represents the value of this counter variable, okay? You must lock it. If you want to look at it, you want to touch it, you want to do whatever. Notice I'm making a copy of it in here, all right? We'll come back to that in a second. Lock it, do stuff with the counter, unlock it. When I'm done unlocking, I can then spend as much time as I want over here processing that row. So presumably, this is where I would add up all the columns. I'll leave it as a task to the student to figure out how to write a for loop that adds up some columns, all right? So what do we got in here? First of all, what the heck is that doing in here? Well, it turns out if you never use this variable, and we haven't talked about it yet, but if I have it, right, at the top of the loop here, let me get the while loop on the screen. There we go. I have this count copy variable up here. And I set it to a value inside this locked region. Down here, I never use it unless I turn on this, debugging statement here. Okay? Now, presumably you would use this. What is this for? Okay? We'll see this represents the row number that needs to be processed by this thread. Okay? Because we can't use counter unless we're holding a lock. And if we keep the lock the whole time we're in this loop, we're serializing our program. So look what's going on in here. Well, a couple of simple assignments and one subtraction. That's all we're going to do when we hold the lock. When we're done with the lock, we're going to ask, did what happened in here, and we'll talk about it in a minute, end up putting us in a situation where we're done? If not, we have something to do. What we're going to do is process the row that's in this variable here. And when we're done, we're going to count, hey, I processed a row. And I'm going to add one to my tally. Now, in this case down here, we can turn this on. We can print it out if we want to see what each thread does. And that's fine. So this printing down here might actually stand in to substitute for the kind of work that the thread needs to do. Okay? Now, notice that when it's doing work down here, again, I cannot emphasize enough that you lock and unlock the counter here for a very short period of time, decide if you want to keep going, and if you do, you want to decide which row you're going to process down here. Okay? If you don't want to keep going, you're going to set count or the done flag to true to let this guy down here know he's not supposed to do anything. Okay? So let's take a closer look at what's in here and why this works and how it works. First of all, we come to the top. We notice that the counter here is volatile. Okay, absolutely needs to be volatile. Why? Because more than one thread needs to use this variable at the same time. Whenever that's true, you must make it volatile. Okay? You'll just get into a world of agony otherwise. You might ask why the heck this is not volatile, because they all use this thing, right? Well, not really. Okay, remember that that vector is such that inside t count, only one element in t count is used by each thread. Therefore, there's no contention. There's no possibility that more than just the current thread will ever touch the element that's represented by the thread ID number that gets passed in. Okay? Now, when in doubt, if you're having trouble, just go ahead and make it volatile. You could argue, yeah, go ahead, I'll make it volatile anyway. Okay? Yes, it will work. But what's the downside of putting volatile in there unnecessarily? Well, what's going to happen is it's going to cause the compiler to have to read the value out of that array, out of that vector, I should say, every single time it wants to add 1 to it. It prevents the compiler from being able to optimize this line of code here by putting tcount sub tid into a register, adding 1, adding 1, adding 1, adding 1 in this loop the whole time, if it has enough registers to do that. And then down here, when the function ends, write it back into that variable once and only once. This code will run faster if it is not declared as volatile. All right? So it also suggests that you don't know what you're doing. Okay? So do not waste your CPU time by putting volatile on variables that should not be declared as volatile. Okay? When in doubt, go ahead and add 1, but keep in mind that that's going to slow your code down. All right? You never want to put extra junk in there if you don't need it, because no matter what it is, it'll either complicate something or slow it down. All right? Now, it turns out that we're doing an awful lot in here. And if we actually write a loop and sum up a bunch of elements or call subroutines, like print something out on the screen, this is an enormously complex process, printing things on the screen, I'm saying. And therefore, I happen to know for an absolute fact, if we do this in here, we absolutely are not optimizing the access out of this array. I mean, if you know how the compiler works, and you know how many registers are in this current machine, I'm running this on a Pentium class machine or Intel or whatever, those iCore or whatever they call it now. I don't even lose track. The point is there's not a lot of registers in that CPU. Therefore, I know that it's impossible for the compiler to optimize this into a single register and keep it there while the loop is running and blah, 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 blah. So it's really not going to do it anyway, especially if I do this in here. If I put a 0 here, it might optimize that to the point where it could do that. You know, a machine like a RISC-V that has 32 registers in it could have enough to optimize this, all right? So bottom line is try to help the compiler not slow down your program, okay? So enough of that. Let's get back to this. What are we doing in this loop? Well, if we are not yet done, we lock access to the counter. We say, okay, is there work to do? If there is, I can -1 here. This is going to be done. It'll be read. The comparison will be done because I'm holding this lock. No other thread can look at the counter. No other thread can be subtracting. This is completely independent. It looks like an atomic operation. It's a very complex one. But because I have a lock here and I have an unlock down there, and by convention, every thread that tries to use the counter for anything whatsoever holds this lock while it's touching it. So that makes this into one big atomic operation, is what it's really doing. Stop the world. No one else is allowed in here while one thread is going. All the other ones have to wait. Preferably, all the other ones are down here doing something unrelated, and they're not really blocked. Okay, that's the goal here. Spend very little time in the locked regions relative to the amount of time you spend, adding up all the columns or something down here. If you think about it, that requires a lot more time than it does to execute these 5 or 6 trivial little statements up here, right? Okay, so that would be good. All right, so what are we doing? We're saying, is the counter big enough that there's actually work to do? If so, we subtract 1 from the counter. Otherwise, what has happened is we've come around our loop, We don't know that we're done yet because we haven't checked the counter. We come in there, we lock the counter, we ask, is it bigger than 0? And if some other thread or threads have already finished the thing, counter will equal 0 in this scenario here, okay? If it equals 0, we don't want to keep going. So we go to the else and we simply say, okay, I'm done now. What row we are going to sum up in this example application is determined by this calculation right here. If we do any summing at all and need to finish is determined by this situation here. Now you've got this going on. Why do I make a copy of the counter inside this lock? Well, it's because down here we want to be able to print it out, or if we're going to sum up all the columns in a matrix, we need to know which row was assigned to us when we subtracted 1 from the counter right here. So we have to keep a copy of that. And we have to make this copy while we're holding the lock. Because if we make this copy down here, something else could have touched it between the time we unlocked it and the time we made our copy down there. Or if we just use it directly, okay? That's just broken. That was the last example, okay? So the goal of this example is to get it right. Okay, so what are we doing? We're keeping a lock on the counter variable anytime we touch it. And if we want to remember what it was while we had the lock, we have to make a copy of it so that down here this code could use it if it wants, okay? And right now, I'm going to just print it out like this. So let's go ahead and run this one. Oops, I tapped it wrong. And I forgot my argument, okay? So what's happening now? Oh, look at that. The work is perfect. We got these two things add up to this number right there. It all comes out. When thread 1 ends, it ends with the count equal to 0. When thread 0 ends, it ends with the count equal to 0. It's perfect, okay? This seems a little odd, though, right? What's up with that? How come all of a sudden the C value, this is the count that represents the row that thread 0 should add up at any given time. Well, it went all the way down to 0, and then it went back up again. Well, is there a bug? Well, not really. If we go back up in thread 1 here, remember there's 1,000 rows here. Look what happened the last time thread 0 ran. Look at these values. 426, 352, 351, 350, 349. What the heck is that, right? Well, this is the last time thread 0 ran through the loop. It did row 349. And 3.1 went up to 350. Thread 1 rather went up to 353. Which is the one that comes before. How come it's doing this weird thing? And then it goes down to 347. They're jumping all over the place. Is it broken? I submit no. Look what happens here. Thread 0, let's ignore all these weirdness because they're all variations of the same theme. Let's look at the very last time thread 0 did anything up here. It did row 349. Thread 1 does a whole bunch of stuff. For the most part, you see it going 10987654321. Okay, blah, 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 blah. Thread 1 finishes up just about everything here, all the way down to 0. And it says, okay, it got to 0. Thread 1 did this many rows. Count to 0, and it's done. Thread 0 is still sitting over here. 348. What did we see up here when we scroll back up like this? Thread 0, the last thing it did before thread 1 started printing all over the screen was 349. So why is this jumbled up? Actually, it's not. If you think about it, what happened here, thread 1 kept grabbing the semaphore to print on the screen. And thread 0 was starved. It doesn't do this perfectly fair, you know. Well, now what we're seeing here is that thread 1 keeps getting the lock back before thread 0 can ever get it. And it does it a lot. Because every time through that loop, remember, it locks the standard out It locks the ability to print on the screen. It's totally unfair. That's life, okay? Thread 0 finally gets a chance to print its message and says, okay, I'm doing 348. Then it comes back around to the top of its loop and it checks, okay, am I done? No, he just did 348. The done flag would not be set in that case, right? So he asks, am I done now? And the answer then becomes yes. He sets his done flag and he finishes, okay? And then when he finishes, he prints out, okay, I'm done now. And the count happened to, strangely enough, it happened to miraculously leap all the way down to 0. It happened because one of the threads kept getting this lock a lot, somewhat unfairly so, but that's okay. That's just the way this thing works. Luck of the draw. One of them just kept grabbing this lock and printing, and then it would unlock, and then it would come back around, and it would go all the way through here and grab it again before the other thread had a chance to grab it itself, simply because it's not fair scheduling, okay? And if you think about how many machine instructions does it take to do this, not a lot, okay? So it can whip around very quickly before it gets back to here. Once it grabs this lock, this is an enormous amount of instructions. It could literally be on the order of 1 million instructions in here to do this. Formatting and printing and queuing it up and putting it into the operating system so that it can draw it on my terminal window and all this other stuff. This is an enormous amount of work to do this, okay? Then it unlocks. The point is that this is probably 100,000 to 1, if not 1 million to 1, more instructions and time spent in here versus the total amount of time it takes to do everything else down here. Okay, so this is a teeny speck in terms of time. This is a mountain of time. And that's not too bad, except for the fact that we have this other lockdown here, and we're still kind of serializing these two threads, right? Now, that's just because the debugging output is turned on. If I turn it off, now what happens is no time is spent down here. We lock it. We very quickly decide if we're going to keep going, and if we do keep going, our count copy over here is going to have the row number that we need to process when we unlock this and continue down here. Okay, we then ask, am I done? No, I'm not done. And there's the row I should process. And when I'm done, I count I did a row and I go back around this loop. Okay, so let's run it again. The debugging output turned off. This will now run much faster and divvy the work up very differently. Okay, run it a bunch of times. You see very different stuff. In fact, I mean, you don't even know which one of the threads is going to end first. Okay, now thread 0 starts running before thread 1 does usually. I would assume that it takes main a little while to start up that second thread. But it actually is pretty fair. It's close to even, you know. Oops. So much for using my history. So with this, we have a proper application. We lock our resources before using them, okay? And we unlock them when we're done. Now, if you make a mistake, like you forget to unlock this thing, what's going to happen there? The compiler can't help you, okay? That's what's going to happen. It's going to sit here. Why? Right? This is what we call a deadlock or a deadly embrace. What happens is if you lock something and you never unlock it, okay? You come back around here, your lock is already locked. What does it mean to lock something that you already locked? Huh? All right, now there actually are flags and options in the machine that actually you could do that if you wanted to. I didn't set that. So it's probably going to cause the process to get stuck here. Because once it's locked, you can't get it again. Or more accurately, once one of these threads locks this lock, the other thread absolutely cannot lock this lock. So by locking it and never unlocking it, I've caused the other thread to never be able to run. And because no one's around to undo it down here, it's just going to sit there forever. Okay? So these have to be perfectly balanced is the point. Same thing would happen if you locked this standard out lock and forgot to undo it down there, okay? You need to balance these things. I've written this code, by the way, very much in the style of how I would use the pthreads library in C, okay? This is not the best, latest, greatest practice for C++. There's another way of grabbing a lock so that when the variable goes out of scope, it automatically unlocks it for you, which is guarantees you not to have this problem when you forget to unlock it, all right? But that requires a little bit more fancy features of C++ than I want to expect of the viewer, all right? If you know what that is, then go ahead and use it, all right? It is better than this. It's safer, okay? But as long as you do it in a way where you always lock it and unlock it, and what goes on inside here cannot cause a problem to prevent you from getting down here. Like, you don't want to return from a function in here. That would be terrible, because you would have locked it and then returned. And a thread, if you return from here, right, the thread that owns this lock will have completely terminated. What does that mean? It's locked by something that doesn't even exist anymore. Bad things happen, all right? So you have to be very careful when you're writing a multi-threaded app. All right, so I think I'm over time as it is. I hope this basic introduction is useful to getting things started and using mutual exclusion semaphores, starting up your threads, shutting them down, tallying up some totals, and coming up with creative ways to figure out how to distribute work between your threads. Thanks for watching. See you next time.